wanted to work through a problem in which we're going to calculate the stored electrical energy of an arrangement of two charges, I'm calling them Q1 and Q2, that are separated by some distances 1 centimeter. And in this particular problem, we're going to calculate the stored energy for the case of two like 3 microcoulomb charges. So they're both positive or they're both negative. They have the same sign. And also the case of a pair of unlike 3 microcoulomb charges. So two 3 microcoulomb charges where one is positive and one is negative. We're going to do those two cases. We're going to do those two cases because it's interesting to compare those two cases. In one case, when you've got like charges, they're going to repel one another. What energy does this arrangement of charge store? The other case, unlike charges, they're going to attract energy. Attract each other, and what energy does that store in that attractive case? We're asked to solve this problem based on two equations. I want to say a few words about those two equations first. One of them we met when we defined the electrical potential. We said that the electrical potential difference between 2 points, we called that delta V, can be defined as the electrical potential energy difference of a charge moved between those 2 points divided by the charge of that charge, or what we might call a test charge. So this is an equation that defines electrical potential difference. It's an equation, importantly, that reminds us that only potential differences are physically significant. It defines the electrical potential difference, delta V, in terms of an electrical potential energy difference of a charge at these two different positions, two different locations. So we're going to be using that. The other equation that we're going to be using is the electrical potential of a point charge, of a single point charge. We met the equation for the electrical potential of a single point charge. It's K, the Coulomb constant, times the charge, divided by the distance from the charge. And we normally write that as V equals KQ divided by R. Now, I should be careful here. We should be careful here that although we typically write the equation for the potential of a point charge as just V equals KQ divided by R, what that equation means is that the potential difference at some distance r from the point charge, that potential difference from infinitely far from the point charge is KQ over R. So although we're writing just V equals, it's really a delta V, a change in V. It's the change in V between the location R, a distance r from the point charge, and a location that's infinitely far, very far. So I drew a sketch of the problem here. It shows a charge on the left, a charge on the right. This is our pair of charges. I called them Q1 and Q2. It shows them separated by 1 centimeter. And as I say in this problem, in one case, we're going to think of them as being like charges, say both positive 3 microcoulombs. In the other case, opposite charges, one positive, one negative, 3 microcoulombs. Before we solve numerically the energy that's stored in this arrangement, let's actually just talk qualitatively about the energy stored in this arrangement. If these two charges are like charges, so if they're both positive or they're both negative, to position these charges in the neighborhood of each other, for them to be in the presence of each other, we have to push those charges together. We have to force those charges together. When we push those charges together, we do work. When we push those charges together, we're transferring energy. That energy, that work that comes from us, is the energy stored in the final charge arrangement. That energy stored for like charges that are repelling each other, where we had to push them together, is a positive electrical potential energy. So With like charges, this arrangement is storing positive electrical potential. It's greater than zero. For example, if you let go of them, they would fly apart and they would turn that stored electrical potential energy into the kinetic energy of the flying apart charges. In the other case, where one is positive and one is negative, those two charges attract one another. You don't need to push them together, they fall together. In that particular case, where the two charges are opposite and they fall together, they store negative potential energy. You can see that they store negative potential energy. You can understand they store negative potential energy, because if you were to try and pull those close by opposite charges apart to separate Q1 and Q2, you would have to pull them apart to separate them. So to pull them apart, you're going to have to do work. You're going to have to transfer energy to overcome that negative stored energy in that arrangement. So in that case, where Q1 and Q2 are opposite charges, we think of them as stuck together, bound together. And whatever that sticking energy, that binding energy, that stored electrical energy is, we would have to do that amount of work, transfer that amount of energy. Okay, so let's work through the case of two like charges. I'm just going to. In the case of two like charges, we said that the arrangement will store positive electric potential energy, which could be released if we let the charges go. So let's calculate that positive electrical potential energy. The way I'm going to solve this problem, and the way I'm going to solve the problem involving the opposite charges, is that I'm going to imagine actually assembling the charge distribution. So in the picture, you can see the charge distribution, but what I'm going to actually imagine doing is bringing in one charge and then bringing in the second charge so that they're in the neighborhood of one another. Now, I could bring in charge number one first. So here I am. This is an arrow indicating me walking into the drawing pad from far away. I bring in charge number one, and then I could bring in charge number two. Here I am again, bringing in the second charge from far away, from somewhere off the drawing pad into this region with charge Q1. So I could do it that way around. I could do it the other way around. We get the same answer. We get an equivalent answer. So in the other way around, I would first bring in this charge on the right-hand side, and then I'd bring in parentheses here this charge in on the left-hand side. So either way around is fine, and we'll just do the one on the left first and do the one on the right second. Now, as I bring them in, the two charges in, what I'm going to be tracking is the amount of energy it costs me to bring them in. And I'm going to figure out the amount of energy it costs me to bring them in using that equation that the potential change in potential energy when I move a charge upstairs here is determined by the change in electrical potential between the two locations from which I move the charge from and to. It's this relationship here. So this tells me how to connect when I move a charge, how much the potential energy changes if I know the change in electrical potential. So we're going to use that equation. So the question becomes, when I move in charge number one from off-screen to on-screen, what was the change in potential? Then I can figure the change in potential energy. And the second part of the question becomes, when I move in the second charge, the right-hand charge, Q2, from off-screen to on-screen, what is the change in potential? And therefore, I can figure the change in potential energy. So just to make it clear, got a demo. I've got a pair of charges. Actually, I want like charges, don't I? So I've got here a pair of like charges. These are two positive blue charges. This is the charge arrangement I'm going to build with them 1 centimeter apart, with them being 3 microcoulombs each. But the way I'm going to do it is they're over here. and then I'm going to bring in this first charge, and then I'm going to bring in this second charge. When I bring in the first charge, I'm going to figure out the cost in energy, how much work I had to do, how much energy I had to transfer. When I bring the second charge, I'm going to figure out the cost in work, the cost in energy transferred by me. And when I figure out those two costs in energy, the total of it will be equal to the stored electrical energy of this arrangement of two nearby charges. So that's basically my plan. So let me start by writing down an equation to get that going. The change in electrical potential energy. That change in electrical potential energy in building the charge arrangement is going to be equal to the change in electrical potential energy when I bring in the first charge. So I put a subscript 1, plus the change in electrical potential energy when I bring in the second charge. And so I put a subscript 2 on that. And as we said, the change in potential energy when I move a charge from one location to another location. In this case, I'm moving a charge from far away to nearby. That change in potential energy, I can write in terms of the change in electrical potential. And so let me just take that step. I'm going to replace the change in potential energy of charge number 1 using this equation here. I'm going to rewrite it in terms of the change in electrical potential for charge number 1. And so Q1 delta V1. And then I'm going to write for the second charge here. When I move that in, I'm going to write its change in electrical potential energy. I'm going to write that as its charge times the change in electrical potential that it experiences. Well, so now the question becomes, when I bring in this charge from far away, this first charge, what is the change in electrical potential? As I moved it from here, far away, over to here, in the middle of the whiteboard. And then the same thing for this other charge, the second charge, charge number 2. When I move that from far away to nearby, the other charge, what is the change in electrical potential in this case? So we've got 2 changes going on here, this one here and this one here. You can see that they're different changes because when I bring in this one, there's no other charge around. When I bring in this one, there is the first charge around. And that's an important difference. That's an important distinction here. Okay, so let's bring in the first charge. Imagine here is an electrical landscape. What does that electrical landscape look like before I bring in the first charge? It looks like a perfectly flat electrical landscape. There's no other charges around. The electrical potential is just constant. And we can think of that electrical potential as being 0. And so I bring a charge, the first charge, from far away, where the potential is 0, into the whiteboard, where the potential is also 0. So delta V1 for the first charge is going to be 0. That's the delta V1. It's going to be 0. What about the second charge? Second charge is far away right now. It's over here on the right. And I'm going to bring that in and put it near the first charge. What is the change in potential, delta V2, for that second charge? That's not 0. It was at 0, and now I brought it in close to the first charge. I placed it, or it's acquired a change in potential that is given by that formula for the potential of a point charge. It's going to be Q1 over R. It's a distance R from Q1. Q1 is creating electrical potential in its neighborhood. And so it's this second charge, as I moved it in, it does experience a change in electrical potential. And so let me add that idea to this calculation, that when we brought in the first charge, the change in potential delta V1 for the first charge, that's actually 0. When we bring in the second charge, the change in potential for the second charge, that is non-zero. It's moved into the potential of the first charge, which is given by KQ1 over R. Well, at this point, we've got an equation for the change in potential energy in assembling these charges, which is going to be the potential energy, electrical potential energy of the arrangement of charges, in terms of quantities we know, the charges that we've assembled, that's the Q1 and the Q2, and the distance that they are apart, that's the R in the denominator here. And so I can just fill in those quantities. I could write this equation more compactly now. It's just K, the Coulomb constant, times the product of the charges divided by R. And if I fill in all the numbers, so I'm going to fill in 9 times 10 to the 9 Newton meters squared per Coulomb squared for the Coulomb constant. I'm going to fill in the charges. They're both 3 times 10 to the minus 6 coulombs. They're both positive in this case. And I fill in the denominator, I fill in 1 centimeter, so 0.01 meters. If I fill in all of those numbers, this comes out to be positive 0.1 joules. And that's the energy stored by those two like charges. Note, it is positive. We had to do work. We had to transfer energy to assemble that arrangement of two like charges. It is storing positive electrical energy. If I was to release those two like charges, then that 0.1 joules of electrical potential energy would turn into kinetic energy of the two charges flying apart from one another. So that's the case of the like charges. What about unlike charges? Well, it's the same idea that we're going to imagine assembling the arrangement of unlike charges. And we're going to keep track of, add up, the changes in electrical energy. So calculate the total change in electrical energy as I bring in the first charge. So there'll be a change in potential energy. I call it delta PE1 for the first charge, and the change in potential energy associated bringing in the second charge. Again, we're going to rewrite the changes in potential energy between these locations that are far away and nearby. We're going to rewrite them in the terms of the potential difference between the locations that are far away and nearby. So here's the change in electrical potential energy of charge number 1 when I bring it in. It's the product of the charge it owns times the potential difference between where it started and where it ended up. Here's the same thing for the second charge. Again, product of its charge and the change in potential it experiences as we carry it in. Now, again, that makes us think about, well, what is delta V1 and what is delta V2? So let's just think about that a bit. Now I've got my opposite charges. So I've got a negative charge in red and a positive charge in blue. This is the arrangement that we're going to make, but we said we're going to start with charges far away. We're going to bring in the first charge. What's the change in potential for that first charge? We're going to bring in the second charge. What's the change in potential for that second charge? We're going to find those changes in potential, which allow us to figure out the amount of work we do or energy we transfer bringing in the first charge, the amount of work we do or energy we transfer bringing in the second charge, and hence we'll be able to compute, total up the total energy stored by this particular arrangement of opposite charges. So let's go ahead and do that. When we bring in this first charge, here we go, far away, nearby, the electrical landscape that we're bringing it from and into is just a flat, perfectly flat, constant electrical potential. There's no hills, there's no valleys, perfectly flat. So I bring this charge in, it's perfectly flat electrical potential. There's no change in electrical potential. Delta V1 is 0. There's no change. When I bring in the second charge, the positive charge over here on the right-hand side, however, I'm bringing that into the region where there's a negative charge. That means that I'm bringing that into the region of the negative charge's electrical potential. And so this charge, the second one I bring in, does experience a change in potential. That change in potential is determined by the potential of the negative charge here. It's going to be given by that formula, KQ over R. So let's fill that idea in, just like we did for the two like charges. Q1 is multiplied by the change in potential experienced by Q1 as we bring it in, but that was 0. When we bring in Q2, Q2 is multiplied by the change in potential that it experiences when we bring it in. And that's the potential of the first charge. So that's going to be KQ1 over R. And so here we have, we fed in the changes in potential, understanding the potentials of point charges and the electrical landscape in our particular problem. And so now if we look at this equation again, we know the Q1, we know the Q2, we know the separation of the two charges, 1 centimeter, and of course we know the Coulomb constant. So we can just go ahead and calculate the result. I can write this more simply at this point. Again, it's just K Q1 times Q2 over R. Now, the sizes of the charges are the same. The separations are the same as the like charge case. Coulomb constants, of course, the same. There's just one tiny difference here, one but important difference here, is that one charge is now positive and one is negative. So when we multiply Q1 and Q2, instead of getting a plus sign, which you get from the like charges, we're now going to get a minus sign from the opposite charges. So there's no need to redo the sum and calculate 0.1 joules because all the sizes are the same. We just need to change the size. Sign is going to be minus 0. In this case, the minus sign is telling us an interesting thing about the arrangement of opposite charges, that the arrangement of opposite charges actually stores negative energy, negative electrical potential energy. So what does it mean to store negative electrical potential energy? What it means to store negative electrical potential energy is that it would take energy, you would have to add energy, you'd have to do work to pull those charges apart. And that makes common sense, really, because those two charges are opposite, those two charges are attracting, those two charges are kind of bound together, they're stuck together. And to pull them apart, like pulling apart the electron and the proton and the hydrogen atom, you'd have to add energy. You'd have to overcome that negative stored potential energy to release those charges back. Anyway, I wanted to work through that example of calculating the electrical potential energy for an arrangement, in this case, a pair of charges, and we did the case of positive like charges and a positive and negative unlike charge. You could extend this procedure, right? It gets a bit laborious, but you could extend this procedure to 3 charges, to an arrangement of 4 charges, or in principle, an arrangement of any number of charges. To calculate the stored energy, electrical energy, you just one by one keep bringing in charges into the potential of the other charges that are present already. So the procedure, the method is perfectly extendable to 3 charges or 4 charges or more. It just gets more and more and more laborious to make the calculation. We found some interesting results. We found when we computed the values of the stored energy, we found that it was a positive stored energy if you had like charges. And that made physical sense because we had to literally push them together and they would naturally want to fly apart and release their energy, potential energy. Whereas in the case of unlike charges, they wanted to fly together. They flew together and we would have to add energy to pull them apart. It is a nice example of nature's natural trend is to release potential energy, give up potential energy, turn it into kinetic energy. When you got the two positive charges sitting next to one another, they want to release their potential energy by flying apart. When you got two opposite charges that are far apart, they want to attract one another, come together, closer together, again, to release, to decrease their electrical potential energy. So the trend is, whether you got like charges or positive charges, if you don't interfere, things will either fly together or fly apart. But what they're doing is trying to lower or make more negative their electrical potential energy.